Up to this point in calculus, we've been studying limits. Now we are going to shift gears to the next major topic of calculus, derivatives. In this video, we will introduce derivatives by discussing their formal definition and formula, mastering the first type of derivative problem, and exploring some real-world applications of this knowledge. Suppose we have a graph of a function such as this one. And suppose we are interested in finding the tangent line at a given point. When I say tangent line, I'm talking about the straight line that touches only that exact point of the function. For example, at this point, the tangent line would look like this. Or at this point, the tangent line would look like this. Again, the tangent line can only touch the function at that one point. Additionally, notice that from these examples, the tangent line must have the same slope the function does at that exact point. So this would not be an example of a tangent line because it has a different slope than the function, which would cause it to intersect with the function in a second spot. So a tangent line gives an indication of the slope of a function at a specific point. How would we find that precise value, though, apart from drawing the line by hand or by making guesses? That answer can be found by using the derivative formula, which is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. The letters f apostrophe x are typically pronounced f prime of x, and they refer to the function that describes the slope of f at the point x. F prime and this concept of finding the slope at a specific point are key to the topic of derivatives. Let's apply the derivative formula to an example. Find the function f prime describing the slope of f of x equals 3x. So to find our derivative, we're going to use our derivative formula. So let's write that out so that we can remember it. Our derivative formula is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So now we're going to use our function f of x to plug in our values into our formula and solve. So we'll have the limit as h approaches 0 of f of x plus h. We're going to plug in x plus h anywhere we see an x in our function. So we'll have 3 times x plus h minus f of x is 3x, all over h. This may look complex, but we can simplify the numerator before we need to bother with the limit. So we're going to start by distributing the 3 over the x plus h. So that will give us the limit as h approaches 0 of 3x plus 3h minus 3x over h. Now we can see that our 3x and our negative 3x will cancel each other out. So we're left with the limit as h approaches 0 of 3h over h. Then our h's will cancel each other out, and we'll have the limit as h approaches 0 of 3. The limit of any constant is that constant, so our answer is 3. Intuitively, we already knew this to be true, because m, the slope of the line, was set to equal 3. So f prime of x, or our derivative of the function 3x, is equal to 3. Let's try applying the derivative formula to another function. Find the function f prime, which describes the slope of the function f of x equals x squared. We're going to start by writing out our derivative formula. So our derivative formula is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So for f of x plus h, we're going to plug in x plus h anywhere we see an x in our original function. So this is going to be equal to the limit as h approaches 0 of x plus h squared minus f of x is x squared over h. Before worrying about the limit, we're going to again simplify the numerator as far as we can. So we're going to first FOIL out the x plus h squared. So before we FOIL, we're going to rewrite that as the limit as h approaches 0 of x plus h times x plus h minus x squared over h. And now we can FOIL. So we'll have the limit as h approaches 0 of FOIL stands for first, so x times x is x squared, plus outer, x times h is xh, plus inner, which is h times x, plus last, which is h times h, which is h squared, minus x squared over h. So now we can simplify this just a little bit. So we'll have the limit as h approaches 0. Our x squareds will cancel each other out because one is positive and one is negative. X times h and h times x are actually the same term. So we can simplify this to 2xh plus h squared over h. Now from both terms in the numerator, we can factor out an h. So we'll get the limit as h approaches 0 of h times 2x plus h over h. This h cancels out with a 1 in the denominator, so we're left with the limit as h approaches 0 of 2x plus h. We can't simplify this any further before dealing with the limit. Fortunately for us, though, this one's pretty easy. As h gets smaller and smaller towards 0, we approach 2x. So the limit as h approaches 0 of 2x plus h is equal to 2x. So that means that our derivative function, f prime of x, is equal to 2x. Let's see how our solution holds up. The graph of f of x equals x squared looks like this. At the point x equals 0, the slope should equal f prime of 0, which equals 2 times 0, which equals 0. Sure enough, the curve is flat at that exact point. Similarly, at the point x equals negative 2, the slope will be equal to f prime of negative 2, which equals 2 times negative 2, which equals negative 4. We can draw the tangent line and see that this is correct. Feel free to check the solution on your own at additional points. Now that we know how to apply the derivative formula, I want to briefly explain why it works. Let's look at the formula again. Remember when you learned about slopes in algebra? The way we calculated a slope then was dividing the change in height by the change over the x-axis. Some students use the phrase rise over run to remember this relationship. Here, the numerator of the derivative formula helps us calculate the change in height between the 2 points on the curve, the rise. Then the denominator h describes how far along the x-axis we are moving, the run. So the fraction within the limit is itself a way of describing slope because we can look at it as another way of saying rise over run. Now, the limit tells us that h must get smaller and smaller towards 0. This means that we are considering the slope in smaller and smaller increments and getting closer and closer to finding the instantaneous slope of the function. Now that we've used the derivative formula a couple of times, we can see that it typically isn't difficult to use. Just plug everything in, simplify, and then take the limit. But there's something I haven't shared with you about derivatives yet. There's an easier and faster way to solve for f prime of x. The trick I'm about to show you is called the power rule. It states that whenever a function f of x is in the form x raised to some power n, then f prime of x is equal to n multiplied by x raised to 1 less power. Going back to our first example in the video, we had the function f of x equals 3x. We computed its derivative using the derivative formula, but let's solve for f prime again now using the power rule this time. So even though f of x has a coefficient of 3, we can still apply the power rule because it has x raised to some power n. In this case, n is equal to 1. So we're going to have f prime of x is equal to n times x to the n minus 1. So in this case, we're going to have 3 times n is 1 times x to the n minus 1, so 1 minus 1. This will simplify to 3 times x to the 0. Anything to the 0 power is 1, so this is equal to 3 times 1, which equals 3. So f prime of x is equal to 3. This is exactly what we got earlier using the derivative formula. Now let's apply the power rule to the other example from earlier. Finding the derivative of f of x equals x squared. In this case, x is raised to the second power, so n is equal to 2. So we'll plug this into our formula. F prime of x is equal to n times x to the n minus 1. So this will give us n is 2 times x to the 2 minus 1. 2 minus 1 is 1, so we'll have 2 times x to the first power, which is equal to 2x. So our derivative, f prime of x, is equal to 2x. This is the same solution we got earlier by using the derivative formula. I want to finish this lesson with a real-life example. One thing about derivatives that makes them fascinating is that they perfectly describe the relationship between speed and displacement, particularly when speed is varying. For example, if you're given a function that describes an object's displacement, you can also determine the object's speed by taking the derivative of the displacement function. Let's use this knowledge to work a real-life example. A soapbox derby car's displacement in feet is described by the following function, where x is in seconds. F of x is equal to 1/4 x squared plus x. Determine the car's speed at 5 seconds by first using the power rule to find f prime of x and then evaluating at x equals 5. Our first step is finding f prime of x by using the power rule. Notice that f of x has two terms, 1/4 x squared and x. This is nothing to be concerned about. We will simply handle them one at a time. For the first term, x is raised to the second power, so n equals 2. So the derivative of this term will be 1/4 times 2 times x to the 2 minus 1. So if we simplify this, we'll get 1/4 times 2 is 1/2, and x to the 2 minus 1 is just x. So we'll have 1/2 x. Now the second term is just x, which is understood to be raised to the first power. By the power rule, we multiply this 1 in front of the x, so 1 times x to the 1 minus 1. So we'll have plus 1 times x to the 0 is just going to be 1, so we'll have plus 1. So the reason that I just added the derivatives of these two functions was because of what's called the sum rule for derivatives. So that says that if you have a sum of two different parts of a function, you can then take both of those parts' derivatives and add them together, just like we did. So we now have the speed function f prime of x is equal to 1/2 x plus 1. All we have to do from here is plug in x equals 5 to find the car's speed at 5 seconds. So f prime of 5 is equal to 1/2 times 5 plus 1. 1/2 times 5 is 5/2 plus 1 gives us 7/2. 7/2 is equal to 3.5 as a decimal. So at 5 seconds, the car is moving at 3.5 feet per second. As we've seen in this video, derivatives can be calculated using the derivative formula or by applying the power rule whenever the terms of f are in the form x raised to some power. Now you have the tools you need to start working on derivatives yourself. Thanks for watching and happy studying.